Good morning, everyone. Welcome to this edition of the IISER Mohali Public Outreach Talk Series. This is the seventh in the series. And just a reminder to everyone that every single one of these talks is available on the IISER Mohali YouTube channel for you to go and watch. Today's talk is about microreaction technology, a small better. Today with us, we have Professor Vijaya Anand. Vijaya Anand is the Dean of Research and Development at IISER Mohali. He is a chemist, a synthetic organic chemist, and he is the Associate Professor of Chemistry in Department of Chemical Sciences. Vijay did his master's from Anna University in Applied Chemistry, then went on to get his PhD from IIT Kanpur. Then he did his postdoctoral fellowship at the West Chem University of Strathclyde, Glasgow, UK, followed by another postdoc at Texas A&M University at College Station, USA. He then joined IISER Mohali way back in January of 2010. And then ever since that, he has been with us. Of course, he has a large group. They are interested in synthetic organic chemistry. Other than that, he's also an excellent photographer. He loves taking photographs of really small things. So he's a specialist in macro photography. He rubs it in by doing all his photography with a handheld lens, no special machinery. Wonderful photographer. If you are interested, that is also available for you people to view. I would now request Vijay to start his talk. And before he starts, reminder to our viewers, we will hold the questions till the end of the talk. Those who are on Zoom can use the raise hand features and we will let you ask your questions. Those who are on YouTube, you can type in your questions in the comments box and we will pick up those questions and ask them for you. Professor Vijaya Anand.
Thanks, Prasad, for the kind introduction. And good morning, everyone. And first of all, I would like to thank the outreach team, especially Mahua, Prasad, and Amit, for giving me this opportunity to talk about a general topic, which is called microreaction technology, which is also one of my research interests. So today I'm going to talk about the advantages of microreaction technology, especially in organic synthesis. And before going into the details, first I would like to talk about the batch process, and this is the outline as you can see here in this slide. So first I will talk about the differences between batch reactor and continuous flow reactor, and what is microreactor, advantages of microreactor, applications of microreactors, and finally conclusion. So if I want to talk about continuous flow chemistry using microreaction technology, I have to introduce you to batch chemistry. For chemists, I don't have to, because people know about it because this is what we do in our research labs. But for non-chemists, I would like to brief a little bit about the brief chemistry, what is exactly going on in our research laboratory. So this is really relevant, if I want to talk about the advantages of the continuous flow technique. Okay, so in typical experiment in our lab, what we do is that take the reaction flask, you can see here, and then we add the starting materials, reagents or reactants in this flask, and then we add solvents, and then you have to stir the solution properly. There are two ways you can do that. We can fix the external stirrer unit here to stir the solution properly, or we can just put a magnetic bead inside the reaction flask, and then we place this whole setup on a stirrer, and we can just stir it. So that takes care of the uniform mixing of the reactants. Okay, and then after the reaction is over, so you can closely monitor the reaction by using thin layer chromatography techniques. We used to call it as TLC, and you can just monitor very closely the reaction. So once the reaction is over, the TLC will tell us actually the progress of the reaction. So once the starting material is completely consumed, we stop the reaction, and now we need to take out our product from the solution. Suppose if you use some inorganic reagents, so you have to get rid of that inorganic reagents from the product. So for that, we need to do workup. So what we generally do is that we transfer this solution into a separatory flask and then add water and then extract it. So all the inorganic material and other impurities will go into water, and then we collect the organic layer and then evaporate the solvent by using rotary evaporator, and still that product is actually a crude product that may contain the unreacted starting materials or some byproducts. So we need to purify your product from these unwanted byproducts. So for that, we need to use column chromatography technique. So we load this column chromatography. You can just have like silica gel or alumina as a mobile phase, as a stationary phase, and then we just load our compound here at the top of this column, and then add some solvent and then purify it. So finally you get a pure product with the solvent, and then you evaporate the solvent, you get a pure product. And then if you want to do some multi-step reactions, you take this product and then put it in another flask, and then you follow the same process to get the clean product. This is the way we do in our research labs. Okay. So now coming to the continuous flow chemistry. So what we have here is a microreactor. So the picture is given here for clarity. You can just see here. And in this particular technique, what generally we used to do is that we used to just pump the starting materials inside the microreactor, and then the reaction actually takes place in these channels, micro channels. I will come to that in a minute. And then the product comes out from here. Suppose if you want to do another reaction, so you can directly inject this product into a catalyst column or whatever. And then again, the reaction takes place over here and the product comes out. And if we use some specific scavenger columns to scavenge the byproduct or the impurities, so these two will take care of that. And then finally the clean product comes out. So most likely you don't have to purify this product. This will be sufficiently pure. So that is advantage of the microreactor. Generally, the continuous flow chemistry, this term is used for all reactions using microreaction technology. Okay, and you can see in this picture, so there are two inlets here, right? So you can see clearly this is the inlet and this is another inlet. So this is where actually we should pump the starting material or the reagent. And now you have a channel here. This is actually a zigzag channel. So this is used for mixing these two components, because this is very important. If you do not mix these two components properly, then the reaction will not take place. And this portion you can see here, this is called a reaction chamber. The reaction actually happens at this, in these channels. And then you can additionally have one more inlet if you want to do a workup, after the reaction. And then again, you can see here, these channels are like zigzag. So because proper mixing will take place over here, the reaction will be quenched in this place, and then clean product comes out. And if you just see the channel diameter of these channels, okay, it will be 100 to 500 microns. That is why it is called microreactor. And the channel length can vary from even 100 microliter, 1 to 10 millimeters. Okay. All right. So what are the differences between batch reactor and microreactor? I have already explained to you, but anyway, so I will explain it in proper way. Here in batch reaction technique, this is the classical way to do chemistry. Still, actually, 99% of the chemistry is relies on batch process. I'll come to that at later stage. And here the reagents are loaded into the reactor, mixed and left to react. And then the product is also will be accumulated here. And once the reaction is over, the product, we can collect the product after the workup. Okay. And what are the key factors we have to focus here? One is that concentration, because the concentration of the reaction mixture should be uniform. So you have to have effective mixing technique here. Otherwise, the reaction will take very long time, or it may, lead to some unwanted byproducts, or there are so many other factors we have to consider. and then the mixing should be proper. So to maintain the concentration and the temperature is very important thing in the batch process, because the temperature will not be uniform, because at the edge or at the surface the temperature will be very high, and in the bulk here the temperature may be very low. So you have to have a proper balance here. So this is very important to consider. And the reaction time, for example, for some reactions, I will give you one example, like the reduction of alkynes to alkenes, okay, Lindlar reduction, for example. So if you just leave the reaction for a long time, so what happens, the triple bond will be reduced to, alkynes will be reduced to alkenes, and then again over reduction will take place. So you will end up with alkanes. So you have to stop the reaction in between. Okay, so you have to maintain or monitor the reaction very closely to just find out the progress of the reaction, and you have to stop the reaction at the particular time to avoid the overreaction. And in continuous flow technique, it's very simple. So reagents are continuously pumped into the flow reactor, and the reagent actually mix over here, and then the product comes out. Okay, and the pressure is a very important thing here, because the reagent will not enter to the microchannel just like that. We have to force it to enter into that. You have to use a syringe pump, so you have to apply pressure to just push the push the reactants or the solution into the microreactor. So the pressure should be optimized. So what I'm trying to say is, if the pressure is very high, so again there is a problem, there will be a problem, so that it will spoil the microreactor or the syringes. So you have to be careful. And the temperature, I'll come to this in the next slide. So another important thing we have to monitor, or we have to take care in continuous flow reaction, is the flow rate. What is flow rate? Which is nothing but how long the starting material stays in the microchannels. That is called residence time. Okay, so that we have to take care. This resident times can be easily calculated by dividing the reactor volume by flow rate. You can see here. Suppose you consider an example. You have A and then B. These two are reactants, and then this gives rise to a product C. Okay, and now if you consider the flow rate of A is 0.25 ml per minute, and B is also 0.25 ml per minute. So the total or the combined flow rate would be 0.5 ml per minute. All right, and if the the capacity of this micro reactor is 1 ml, so you have to consider this formula. So 1 ml divided by 0.5 ml per minute, so it comes around 2 minutes. So which means these two reactants stay in the micro reactor for 2 minutes, right, at a given point of time. Is that clear? And suppose if you want to increase the residence time to 8 minutes, there are two ways you can do that. One is to slow down the flow rates to 0.0625 ml per minute, or to increase the reactor volume to 4 ml. In these both ways, actually the residence time will be 8 minutes. So in this way, actually you can just manipulate. Okay, now coming to the components of microreactor. See, there are several companies who make microreactor setup. Okay, microreactor, this is called microreactor, but you need a setup to do the continuous flow reaction. And you can see here, this is particularly from a from company called Future Chemistry. And so I'm just, I have taken for just explanation purpose. And you can see here, there are three components. One is temperature module, and another one is pressure module, and the last one is photochemistry module. In almost most of the commercially available micro reaction setup, the first two will be a common thing. It will be there, the temperature module and the pressure module. Photochemistry module is actually the extra. So if you want, just you can just purchase, and it's like it's an extra addition. So now coming to the temperature module. What is temperature module? It's nothing but a hot plate. You can see in this whole setup, you can see this is the micro reactor holder. And you can see this is actually the zoomed portion of this part. This is a micro reaction holder, micro reactor holder, and where you can place your micro reactor, and it has like inlets and all. And then this is actually attached with a hot plate here. This is an integrated hot plate, and you can control the temperature here. The controller is also here. So you can go up to 250 degrees. So it's basically a hot plate is attached to that. And since it's like very thin, the heat transfer will be very high. I will come to that in the advantage part. But this is basically the temperature module is a hot plate, which is which is integrated with the micro reactor whole unit. And another one is the pressure module, which is nothing but syringe pumps. You can see in this particular model we have 3 integrated syringe pumps. Okay. And the advantage is that you can control the flow rate separately. Suppose if you want to have like 1 ml per minute, you can set up here 1 ml per minute. And here for the component B, if you want only like 0.5 ml per minute, that also you can just do it, so that the mixing will happen accordingly. Okay. The third one can be used for doing workup and all, as I have already mentioned. You see here, you can see here, this is actually the third one. You can just connect it over here so that you can easily do workup and all. And in photochemistry module, it's very interesting thing. So you have an additional setup, so which can be easily fitted in on the top of this. You can see here, this you can unscrew it and then open it up, and then you can put or you can fix the photochemistry module over here. So there are, I think, if I'm correct, 3 different wavelengths are available, 470 nanometer or 365 or something like that. You can just do photochemical reaction over there. All right. So what are the different types of microreactor in the market? There are several types of microreactor in the market. One is like chip-based microreactor, or capillaries, microstructured, and industrial. So whatever we use in the lab, all are based on chip-based microreactor. Okay, or in some cases you can also use capillaries, and you can see here then chip-based. I already told you how this reaction takes place here. And in capillaries, what happens is that you have 2 inlets, and the reaction takes place over here, and then you get an outlet here. And then according to the nature of the reaction, multi-component reaction also, you can do it by using more number of inlets, attaching more number of inlets here. And in pilot plant, generally we use microstructured microreactors. As you can see here, this is a cross section of that. This is the cross section of this, and you can see here the small the channels here. So the reaction takes place over here. You have inlets and outlets integrated here, and then you can simply do pilot scale reactions. And this also is another example of microstructured microreactor, and this is an industrial scale. So here the diameter of this microchannel will be larger when compared to the lab one. So it is not very efficient, as efficient as the lab or chip-based microreactor, but it is definitely better when compared to the batch process. Okay, so there are different kinds of microreactors available, and basically, I'm just concentrating more on the lab-based, development in this particular area. And there are different types of chip microreactors available. And of course, every company, makes, different microreactors. Just for informing you, I have just, picked few microreactors. You can just see here, this is a basic microreactor. So you have only 2 inlets here, and then the mixing chamber is here, reaction chamber is here, and the product comes out here. And in basic quench microreactor, you will have an additional inlet that is for workup. You can see here, first the reaction takes place here, and then the product comes out. And if you want to quench the reaction, and then you can just use this inlet. You can just, suppose if you want to quench some acids, you can use base here, or if the reaction is under basic medium, and if you want to quench the excess base, you can use acid here, and then the reaction, the quenching process will take place here, and then product comes out. And in short quench microreactor, this is really useful for a very fast reaction. Suppose if A and B just mixes and then immediately it reacts to give the product, you can just use this kind of microreactor. This will reduce the time because this portion is not there, right? So you just mix it, and then the reaction takes place over here very quickly. And then if you want, you can just have attach the another inlet for quenching, and then the product comes out immediately. So there are, there are various kinds, but these are the three main microreactors we generally use in the lab. Okay, so now coming to the advantages of microreactor. So as I have already mentioned, this microchannels, this thickness is very, very less, right? It's in 100 to 500 microns. So that means actually, you have a high surface to volume ratio. You can see this is ideally 10,000 to 50,000 meter square by meter cube. So in the traditional batch reactor, the surface to volume ratio is very less. You can see this is 100 meter square by meter cube. You can just see here, this is the comparison chart, and the chip microreactor is somewhere here because it has a large surface to volume ratio, and the conventional reactor is ideally here. So this is only 100. You can see here that solid foams, monoliths, this is nothing but, a tube, and which is filled with, a kind of filters, so, and then this is actually solid foam monoliths. So you will have a foam in between that, the pipe. Inside the pipe you have a foam, and with some porous materials there, and then the solution passes through it. That is called solid foam monoliths. So that is slightly better than this. And then industrial reactors comes here, and then microstructure reactors, that's slightly better than this, and then capillary reactors better than microstructured ones, and the best one is the chip-based microreactor. So as a result, since it has a high surface to volume ratio, this allows excellent heat and mass transfer. I'll tell you in the next slide. So I'll take an example, and I will explain what are the advantages of microreactors over the batch reactor. Suppose if you consider A plus B, that gives C. Okay. So when you add A and B in the reaction flask, initially you will have more concentration of A and B, or equal concentration of A and B. So it is very easy for A to react with B because n number of B molecules are there in the reaction flask. So the reaction takes place quickly, initially for some time. Once it reaches 60, 70, 80, or 90%, you can see here after 90% conversion, so you will have more concentration of the product C and very less concentration of A and B. So it is very difficult for A to find out B to react, okay, because since it is in bulk, right? So what happens? So obviously, to complete the last 10%, like 90% to 100%, it takes enormous amount of time, very large time. Okay, the time will be very, very large. So that is another problem here with the batch reactor. But in microreactor, so what happens is that, as I already told you, see these two, the concentration of A and B will remain constant, right? And so there is no problem of this kind of thing, like the 100% conversion will take place very easily, because at all times actually the concentration of A and then B both will be there in the microchannel. So A will find B very easily, so the reaction will take place efficiently. So it is possible to attain 100% of conversion with minimum time. And another problem with batch reactor is that since A, B, and C are in the same reaction flask, side reaction between A and C or B and C are possible. Suppose if C is kind of, if it has, multiple functional groups that is incompatible with A and B, so what happens is that, the side reactions are possible. So that would lead to a lot of byproducts. Okay. So that can be minimized, because this kind of problems will not be there in microreactor, because once the product forms C, so what happens is that the back mixing is not possible, because you are always pushing the solution to the forward direction. So the backward mixing is not possible in this particular case. So what happens is that the concentration of A and B, so that will not be there near C. So the C will not react. There is no chance that C will react with A or B, so to give some byproducts. So in this case, so the microreaction technology will be cleaner, so that avoids the byproduct formation. And another important point is the hotspot, especially that happens in reflux reactions, and I already told you in the first few slides. So if you have this bulk, so if it is a reflux reaction, so you apply heat from the bottom or the sides. So what happens at the sides, actually the temperature will be very, very high, and in the bulk actually the temperature will be somewhat low. So what happens, you can always find a hot spot in this kind of reactions. In the hot spot means that those spots actually will have really high temperature. So due to the temperature, what happens, suppose if one of the components, or A or B or C, if it is very sensitive to temperature, at that temperature that will not survive. So that would lead to some decomposition of A or B or C. So again, the concentration of byproducts or impurities will increase in the reaction mixture. So this kind of problems will be avoided in microreaction technology, because it's like very thin. The microchannels are very thin, so that allows actually efficient heat transfer to the microreactor. So as a result, you can maintain a constant temperature throughout the reaction, and then finally that would result in very high excellent mass transfer. So that would eventually lead to the improvement in the yield. Okay, and the last one is chemo and regioselectivity issues. For example, if one of the components, for example A, it has actually two different functional groups, or maybe same functional group, like one primary alcohol, one secondary alcohol. Suppose if we want to acylate only the primary alcohol. So in batch reaction, what happens is that, so the primary alcohol and the secondary alcohol, these two are in contact with B. So there is a possibility of the side reaction. The primary alcohol and secondary alcohol both will react. But of course, the primary alcohol has more reactivity, but still the concentration of B is very high, or B is in very close proximity of the secondary alcohol. So the chances of byproduct formation will be very, very high in batch reactor. But this kind of problems will not be there in microchannels, because at a given point of time, only the calculated number of the acetyl moiety or acyl that electrophile will be available here. So since the primary alcohol is very reactive, first that will react with acylation, the acyl chloride or acetic anhydride, whatever. So that will not allow the secondary alcohol to react. So in that case, actually, you can improve the chemo and regioselectivity issues in the case of microreaction technology if you do that experiment in in continuous flow. Okay, and another important advantages of microreactor is the safety issues. Suppose if you want to make a particular compound which is an explosive compound, for example, here it is per acid, or peroxides. So in that case, you have to be very careful, because the concentration of peroxides will be very crucial. And if the concentration is high in this reaction flask, that may lead to explosion. So in a batch reactor, the possibility of explosion will be very high, because you will have a high concentration of the peroxide or explosive compound inside the reaction flask. But in microreactor, so the product is actually continuously removed from the reaction, right? It's a continuous flow technique, right? So at any point, the only little amount of the product will stay inside the microreactor. All other products will be flushed out from the microreactor. You can just do workup, and then you can just store it very safely. So that is the main advantages of another main advantage of microreactor. And the last one is process optimization. In any organic chemistry lab, suppose if you just find out a reaction which is working, so the first thing we do is process optimization, which means actually you have to find out the ideal condition to maximize the yield of your product. Is that correct? Okay, for that you have to do a lot of reactions, at least 20 to 50 reactions you have to do to find out the ideal condition for the reaction. It could be like the solvent, you can do various solvents, or the temperature. Maybe you can just try one temperature like 30, 40, 50, 60, 70. You have to do like 4 or 5 different reactions to find out the ideal temperature for the reaction. And then the concentration of A and B, right? Like 1:1 or 1:2 or 2:1, something like that. So you have to do separate experiments for all this, to optimize the reaction conditions. But if you have a microreactor, so at least, these two parameters like stoichiometry and the temperature, you can just optimize in only one experiment. You know how? See, for example, you consider this reaction again, A plus B, that gives C, right? And now what you can do, so you can just have the same flow rate for A and B, like 1 ml per minute, for example. So the concentration of A and B will be same, okay, in the microreactor. And right now, I mean, initially you can just do the reaction at room temperature, and then the product anyway it comes out, right? So it's continuous process. So you can just check TLC from the from the outlet. You can just take one drop of the reaction mixture and then check TLC. If there is no reaction, what you can do, you can just increase the temperature to 50 or 60 or 70 or 80, and then you can just wait for the the reaction mixture to come out and then check TLC. So that suppose if at 80 degrees, if the reaction is working, so now you know that at least the temperature can be optimized to 80 degrees, right? In one experiment you can do that. At the same time, what you can do in the same experiment, so you can also change the stoichiometry. For example, you can flush A like 1 ml per minute and then B 0.5 ml per minute, or vice versa. So you can also optimize the stoichiometry of the reaction. So in one reaction, you can optimize two parameters, right? That will reduce almost like 20 reactions, optimization reactions at least. Okay, so that is the advantage of that. All right. So another important thing, how to control our fluids in microreactor. So I'll give you one example. On the right-hand side, you can see here, these two glaciers are, it's like coming like this. It's a typical laminar flow, you can see. And the problem is that actually you can see the mixing is not happening over here, right? These two streams of ice, you can see that mixing is not happening here. If this kind of thing happens in microreactor, there is no point in using microreactor because the reaction will not work, right? So that is why in the microreactor there will be a separate the mixing chamber. You can see here, this is a zigzag, the microchannel is like zigzag. So the proper mixing takes place over here. There are various channels available, geometries available. You can see this is Y junction, T junction, and this is called interdigitated multi-lamellar mixer. So in the tube itself, actually you will have like separate sections. So and then actually the mixing happens over here. Okay. And there are two broad classes of pumping techniques used in microreaction technology. One is hydrodynamic flow, and in this flow, actually this is the principle of most of the microreactors used in laboratories. And you can see at the beginning of the channels, the velocity vectors are equal across the channel, and but further down in channel B and C, you can see the fluid flows faster in the center of the channel than the sides. Okay, this is the actual basic techniques used in all in basically in microreaction technology in the lab at least. And the another one is electro-osmotic flow. So what happens basically at the particular pH, so the walls, the micro reactor walls will be negatively charged. So that will obviously attracts actually positive ions from the solution and forms a electrical double layer. Okay, when an electric field is applied in this direction, so what happens is that actually the electrons actually moves in this direction. So obviously all this positively charged species will be moving it, and it drags all the even the negatively charged species as well along with that. So this is basically used in some pilot scale reactors and even in industrial scale reactors. All right, now I'm coming to the applications of microreaction technology. So I will be concentrating more on some organic reactions. So I have made it, very simple so that even non-chemists will understand. So, so we will discuss, one by one. So we can do two component or multi-component organic reactions here. Or reactions involving reactive intermediates, for example, benzene reaction, or reactions involving carbocations, carbanions, or the radical species or carbenes or whatever. And reactions involving metal catalysis, and that is very important thing. I will just spend some time here. And multi-step organic synthesis, like total synthesis of natural products, and enantio selective reactions, which is very important in organic synthesis, and synthesis of natural products and drug molecules. Applications in process chemistry, this is another important area, actually it's coming up now. And biomedical applications. Okay, so let me talk about very simple organic reactions. For example, the nitration of phenol. Okay, so generally if phenol is subjected to nitration reaction using nitration mixture as a nitric acid and sulfuric acid, so what happens is that we always get a mixture of ortho and para substituted nitrophenols, right? These two will be always there. Okay, of course the para will be a little bit more when compared to ortho, but these two products will be always there. Along with these two products, some polynitrated products are also possible. In batch reactor, generally that is the main problem. So you have to be careful here. This nitration means actually if it is polynitrated, that will potentially act as an explosive, right? Because the nitrogen content is high. So what I'm talking is that actually, along with this mononitrated product, you will have di and trinitrated products as well in the batch reactor. But if you use microreaction technology here, so the excess of that nitration mixture will not be available, okay, inside the microreaction channel. So if you just calculate or maintain the stoichiometry 1:1, so obviously only 1 mole will react with 1 mole of nitric acid, and then the second mole will not be available for the reaction. So in that case, the reaction will stop at the mononitration stage. So that is why if you see this polymeric byproduct reduced by a factor of 5. So that is a major advantage here. Okay. And then another important thing, you can see this is synthesis of ascorridol. So this is basically a drug to expel parasitic worms from the body and plants. Okay, and this is the structure of that, and this is highly unstable compound, by the way. And if you do, or if you make this compound in a batch reactor, so there will be some unwanted reactions because this compound is not highly stable, and also it is explosive. You have to be careful with that while doing the reaction. And so if you apply batch reactor, microreaction technology here, and you see here the yield is increased from 67% to 85%. And then it is actually safe, right? Because you don't have to handle too much of the product in the reaction flask. And then Mukayama aldol reaction, which is basically, you have this fluoride minus will come and react with the silicon, and then you get that, enolate. This portion will come and react here. So you get the beta hydroxy ketones. So in batch reaction, this reaction takes 24 hours, because I have already explained to you initially the reaction will be faster, but once it reaches 80% or 90% conversion, so the reaction will become very, very slow. And and actually you have to the maintain the reaction also properly. If moisture or something is there in the reaction, so that would lead to the decomposition of the starting material. So you have to be careful. So you should not allow this to stay in the reaction flask for a very long time. And in microreactor, the reaction takes only 20 minutes to achieve 100% conversion. And another important thing is Grignard reaction. And generally, if you take this kind of enones and add Grignard reaction, because you know that Grignard reagent is a hard nucleophile and it is like a hard electrophile, it prefers 1:2. But there is another point here. So initially, whatever the Grignard reagent you use, it approaches only this 1:2 position. But if you have a really bulky group which is attached to this magnesium or in this carbonyl group, then 1,4 addition takes place predominantly. And you see here, and this particular reaction, actually 1,4 product is the major product and 1,2 is the minor product. And in the batch reactor is only 49% yield, and the ratio of A and B is 65:35. And in microreaction technology, the yield improved to 78%. Not only yield, you can see the selectivity. The selectivity is very high, 95:5. So it's very important thing to be considered. All right. So another one is Diastereo selective alkylation reaction. This is basically a David Evans chiral auxiliary reaction. and the simple alkylation. You can see this base will deprotonate here, and then alkylation takes place over here. Generally, this gives a mixture of these two compounds, and this is basically a byproduct. The sodium hexamethyl disilocane that hydrolyzes this amide, and then this N minus is coming and attacking here. So the N alkylation will take place. So you can avoid, in flow chemistry, you can avoid the byproduct formation. Okay, so see, there is no byproduct formation in this case, and the selectivity is also improved to 91:9, the diastereo selectivity. And you can also perform peptide bond formation, in microreaction technology. I'm not going into the details. I'll show you simply. You have an acid here, and then this hexafluoroalcohol. It's called deresimizing agent here, and then first it is forming like this ester. This is more reactive, or this makes actually this center more electrophilic, right, because this is a good leaving group. And then the amine is added here. That amine will come and react here, so you get this product, amide. And glycosylation reactions. So this is another important reaction in carbohydrate chemistry. And there are two components here. One is glycosyl donor, and another one is glycosyl acceptor. And in this particular case, what is happening is that, so the TMS triplet, this is trimethyl silate triplet, that actually coordinates with this nitrogen or this oxygen, and then it forms that oxonium ion. And again, this anchimeric assistance, you might have heard about it. So this carbonyl group comes and reacts here, and it forms another what do you call oxonium ion. And then this alcohol comes and reacts either in this place or in that newly formed oxonium ion. So that would lead to two different products. One is glycosylated product. This is the actual product we generally want. And then this is a kind of the impurity. This you have to reduce it. In batch reactor, considerable amount of orthoester was observed, but in microreaction technology, the time is also very, very less, and then it favors only glycosylation product. Okay, that is the advantage of this. Okay, and we can also do photochemical reaction. This example depicts actually 2+2 and 5+2 cycloaddition processes. And in this case, actually melamide is reacted with an alkyne. So you get 2+2 cycloaddition product. And you can see here, this is 83% conversion at 8 ml per minute. This is the flow rate. And in 24 hours, you can get, almost like 700 grams of this product. It is really, really high. So you don't have to worry about it. Suppose if you want to make, around 700 grams of the product, you have to spend almost like, 2-3 weeks, if you want to do it in small scale in the lab, in the batch process. But in continuous process, actually, you can just scale it up to at least, 600-700 grams in 24 hours. That is very good. Similarly, this is 5+2 cycloaddition. So this formally what is happening is that, this is basically 2+2 cycloaddition followed by this ring cleavage. So it's a formal 5+2 cycloaddition process, and it gave like 80% yield. And in 24 hours, one can get almost like 180 grams of this particular compound. This is very, very high. So it's impossible to get this much, at least in lab scale, in 24 hours. And another important thing is metal catalyzed reaction. I told you this is very important reaction, because most of the reactions in organic chemistry is known in the literature is metal catalyzed reactions. And there are two types here. One is homogeneous, and then the second one is heterogeneous. Suppose if you have a homogeneous metal catalyst, which means it is soluble in some organic solvent, you can just follow the simple microreaction technology, whatever I have shown you before. So you can dissolve the metal catalyst in the syringe, and then you can inject to the microreactor, so the reaction takes place in the microreactor and the product comes out. But if the metal catalyst is insoluble in the organic solvent, then you will have to use a different technique. So what is that? You can just pack the metal catalyst in a cartridge. You can see here, this is a cartridge, So it's a micro cartridge. You can just say it's like thickness is very, very small, but inside actually you can just pack this palladium carbon, the catalyst, and then you can inject the solution through this cartridge. So the reaction takes place at this place, I mean, inside the cartridge, and the product comes out. This reaction is simply the reduction of that azides into amines. So that can be done by using hydrogen and palladium carbon. And this is an example of the use of metal cartridges in the reduction reactions. And very important thing is that you can also monitor the progress of the reactions by flow IR technique. This particular example, you can see this is the conversion of an aromatic cyano compound into in an amide by using zirconia as a catalyst. Zirconia is zirconium oxide, so that is used as a catalyst here. So what you do generally, so you inject the cyanide and with water, because water is also required because it's a hydrolysis reaction, partial hydrolysis reaction. And then the reaction actually takes place over here, and then the product actually comes, and then it flows through the flow IR. You can see here, this is flow IR. See, this is the cartridge, and then the starting materials, everything is going inside, and then the product comes out and it is going inside, and again it is coming out. Okay, and you can just collect it in the flask, the product, right? But you can just monitor it. You can monitor whether this reaction is happened or not. So accordingly you can just maintain the flow rate and all those things. So the thing is that the online or the flow IR technique can be used to monitor the reaction online. Okay, and these are some coupling reactions. So the thing is that the microreaction technology is very useful here. I will tell you why. Because if you perform the Suzuki and Sonogashira coupling reactions, especially in drug molecule synthesis, suppose if you want to perform the Suzuki coupling or Sonogashira coupling, you have to be very careful with these palladium levels, because if you do a batch process, it is always very difficult to separate this palladium catalyst from the product, because whatever you do it, so some palladium will be always associated with the product, so it's very difficult to remove it. And if you just use a palladium cartridge technique here, microreaction technology with palladium cartridge, so the product, the palladium will not come out from the cartridge because it's tightly bound with the cartridge. So only the product comes out. So, and you can see here the palladium concentration is less than 2 ppb. It's very, very good. It's a very good application in pharmaceutical industry. Okay. So I'll just go through, quickly. We can also do Enantio selective reactions. This is particularly enzyme catalyzed kinetic resolution reactions. Basically, it's like a ring opening of this epoxide or kinetic resolution. Okay, only 50% conversion will be there. That's the maximum amount, and you have to use a special kind of microreactor here. And the catalyst is injected, and the substrate is injected over here, and the reaction takes place here, and then the product comes out. Okay, and you can see this. I'm not going into the details because I have to complete this presentation by now, so it's almost like 50 minutes. Okay, but this is very useful. You can also do enantio selective reactions here. And total synthesis of oxomaritidine, which is actually a cytotoxic alkaloid. I'm not going into the details, but I will tell you briefly what is happening here. So the first step is simple displacement reaction. But the advantage in this method is that you do not have to purify the product in any stage. Okay. How? Because you see here, this is a cartridge, and it's filled with this kind of polymer. This actually azide is a counterion here. It's a simple displacement reaction. Once you allow the reaction to flow into the reactor, so only this product comes out. And again here, this oxidation. So you send this benzyl alcohol into the reactor, which is having like ruthenium tetroxide. So the oxidation takes place, you get this aldehyde. And then again, we can just pump these two starting or components into this microreactor, which is having a polymer bound triphenyl phosphane or some phosphines. So you get, this is azabatic reaction basically, right? And the byproduct is actually the triphenyl phosphine or some phenyl oxides, like trialkyl phenyl oxide. So that is very difficult to remove it. But in this particular case, since it is bound with this cartridge very strongly, so the byproduct will not come out from the reaction, so that will stay inside the cartridge. Okay, so we can regenerate it later, or we can do some other alternative usage of this. And once you get this product, and then hydrogenation here, and then followed by that acylation, N acylation, you can just see here, N acylation takes place over here. And finally, that oxidative cyclization over here. Basically, what is happening here is that oxygen will react here. So this trifluoroacetate unit will go out. And then basically this center will come and attack here. This moves here and this moves here. Again, that iodobenzene will be the byproduct. You get a clean product here. And then finally, you can deprotect it by using this ammonium hydroxide. And then this nitrogen will come and react here. The cyclization, intramolecular cyclization takes place to get this particular natural product. Okay. So in industry, what generally people do is that, so they develop the technique in the lab scale, and then they take it to the pilot scale, that is around 20 to 30 kilogram scale. So they have to demonstrate it. And then once it is successful, then you just go to the multi-kilogram scale or tonnage scale, right? But here in microreaction technology, you don't have to go to the pilot plant. So directly you just take the lab scale and then go to the industrial scale. But here you cannot, what you can say, you have to number up, right? Instead of having that bigger unit, so you have to number up, right? Suppose if you just like number up like 500 or 600, then it can do the job, right? Okay, so this is another important thing, is our process chemistry. So this is synthesis of fluoxetine, is an antidepressant, and you can see here, so the purification is not much required. And so you can simply do that. The first reaction is reduction, excuse me. And then the second one, so from here to here, it's a simple displacement reaction. The chlorine is displaced with amine. And then again, the third step is actually you have to convert this hydroxy into this aryl ether. So that can be done using Mitsunobu reaction by using isopropyl azo dicarboxylate and then tributyl phosphine as a reagents. So everything you can just do it in microreaction by using microreaction technology, and then you get the clean product out of it. Okay, this is another example. I'm not going into the details because of the time thing. So then coming to our contribution, so we have also used this particular technique for developing some chemical reactions, especially the 1,6 conjugate addition reactions of paraquinone methydes. And you can see here this paraquinone methide is injected here in one syringe through to the microreactor, and in another syringe we have taken dialkyl zinc. So basically this is dialkyl zinc, the alkyl addition to paraquinone methide, and the reaction takes place over here. Resident time is 10 minutes. It's large. I mean, the time is more here because the reaction is slow. But we get 64 to 99% yield of the products. We have lighting examples and we have published it. And another example is like thiol addition. This reaction is very, very quick reaction. You can see the resident time is 3 seconds. You just send the solution, the reaction takes place, and then immediately comes out. So 3 seconds means the reactants stay in the microreactor only for 3 seconds. So it's really efficient reaction, and we get almost like quantitative yield of the product. And in another example, this is alkylation of a paraquinone methide with the nitro alkanes. This also can be easily done. We have 29 examples done, and with 93% of the maximum yield. And another important thing is that you can easily monitor the reaction by looking into the microreactor. For example, in this particular case, the paraquinone methide is highly colored, so it's yellow in color. Okay, and the product is colorless. Okay, and this diethyl zinc is also colorless. And you can see at the beginning of this microchannels, you can see this yellow color, which means actually the starting material is here, right? This is still there. But at the end, you can see here, there is no yellow color, which means the reaction happened already. Okay, so the product has formed at some point here. So you can easily just monitor the reaction by looking into it. Okay. All right. So now I would like to, conclude my talk. The microreaction technology is, as I told you before, it's an emerging technology, and it has been already realized in lab scale and also in process industries to some extent. And this technology involves, processing continuous flow reactions within structured microchannels having a diameter less than 1 millimeter. And due to this, actually, we have a high surface to volume ratio in microchannels. So that results in excellent heat and mass transfer. And the formation of unwanted byproducts could be minimized in the microreactor because the reaction mixture does not stay in the microchannels for a long time. This is another important point I already told you. Due to this, inherent advantages, application of microreactors has been realized not only in simple reactions but also in multi-component photochemical and Enantio selective reactions. But is there any limitation of this particular method? I would say yes, because the reactions which are homogeneous, can be the reactions only if the reactants are soluble in the solvent. That kind of reactions only can be done in microreactor. Suppose if one of the components is not soluble in the solvent, we cannot just use microreaction technology, because since these compounds are not soluble, so it will choke the microreactor. It will go inside the microreactor, it will block the microreactor, so we cannot use that microreactor anymore. So only homogeneous reaction can be done in microreaction technology, at least in the lab scale. Okay, because the microchannels, the diameter is very, very small. So that is the main limitation of this microreaction technology. Okay, with this, actually, I would like to conclude my talk, and I will be very happy to answer if you have any questions. Thank you.
Thank you, Vijay.
Thanks.
We would now like to open up for questions. For colleagues who are on Zoom, if you have any questions, please use the raise hand feature. In the meantime, let me take a question from YouTube.
Okay.
Here's Shweta Sani. Her question to you is, Vijay, using microreactors, can we do reactions which have slow kinetics?
You can do any kind of reactions, because the control of that fluids, it is in your hands. Okay, so you can just speed up the flow rate, or you can just slow down the reaction rate. So you can do any kind of reactions, but as I told you, there is one limitation. Suppose if that reaction is completely homogeneous, that kind of reactions only you can do it in microchannels. Otherwise, we cannot do that. Okay, that is the basic point here.
Okay.
But yes, any kind of reaction you can do.
Anybody else on the Zoom would like to ask a question? Okay. There's one hand up. Sparsh, please go ahead.
Yeah.
Sparsh.
So I wanted to ask that can we check like in situ reaction mechanism while performing a reaction on a microreactor?
That is kind of difficult, because you can just do that once the product comes out, once the reaction. See you in this kind of reactions, the whole reaction is taking place inside the microchannels, right? The product comes out. Suppose you are asking me, is it possible to take some portion of the reaction mixture and then analyze it, right?
In between.
So that is very difficult to do that. Yeah, in microreaction technology, that is not possible. Yeah. Of course, that is the advantage of batch reactor, by the way.
Okay.
So you can just take some liquid from the reaction mixture and then you can analyze it. But in this case, actually, you cannot do that. Yes.
Okay.
Yeah.
Thank you.
Thank you, Sparsh. We'll just wait for a few seconds to see if there are other questions. Let me just check with the YouTube.
Sure.
Okay. Looks like there are no other questions.
Okay.
So I'd like to thank Vijay. Thank you, Vijay. This was
thank you very much.
Very nice talk. I had no idea about these small little reaction things. Very interesting
Okay.
stuff. Thank you so much.
Actually, we have in our lab actually the microreactor setup. If anybody wants to have a look, please, you are welcome to my lab, and then you can have a look.
Thank you.
At the whole setup. Yeah. Thanks.
So thank you, everyone. And special thanks to my colleagues, Amit and Mahua, who are handling a lot of stuff in the background. Thank you all for attending. Thank you, Vijay. Thank you.
Thank you very much. Thank you very much. Bye-bye.